summation right here, so it's still you have -2 over n squared. So you still end up with.
All right, class, let me talk to you about this. Now, I didn't give you a MATLAB assignment. I gave you basically just the homework was basically to just create the actual summation functions and find C of n for a variety of functions. Now, this is only the input. Then you had the filter you had to figure out. And today, what I'm going to do is take you through a typical kind of thing you're going to be doing for me for some extra credit. And I want to show you this in MATLAB. I'll give you the base script, all right? Now, how many have used MATLAB before? Give me a show of hands here. Who has not? You have never used MATLAB in any of your classes? All right. Well, MATLAB is basically a language similar to C or any other programming, but it's a much higher level language. It has all the functions that you need bottled up in it, and it's very easy to use. You're used to for loops, right? MATLAB has for loops. You're going to see one in a second. You're used to indexing things, right? Now, the nice thing about MATLAB is there's no formatting. I don't know if C++ requires it, but I know C does, right? You have to declare things. You have a certain format, integer versus what? Alphanumeric values, and if you're in hex versus, binary, all those things are things you have to declare and do. MATLAB doesn't require any of this. As a matter of fact, it's extremely easy to use. Now, the real strength of MATLAB is that it has toolboxes. And this is incredible power because it has every functional thing you can imagine available to you at your fingertips. And it is a matrix type of operator too, which makes it more efficient. Now, I wrote this thing in a very crude way. First, this is the waveform I'm trying to actually go ahead and manipulate. Now, if you take a look at this, can you all see it all right? I'm assuming you can. I blew it up, and that's rough. Let me do it. I can make this thing a lot smoother here. As a matter of fact, I'm just going to increase the number of terms, make that 300, and make that, say, 180. I'm not sure how long this is going to take, but it should be almost instant, hopefully. Come on. There. Now, I'll explain something, too, with this. I'm not using, I've got a fairly coarse grid in time. And what you're seeing here is, you see this little jump right there? What it is, that is numerical error caused by me picking a point here that doesn't correspond to the same point here and here where the transition occurs. Do you understand, class? Now also, the number of spacings here, I took this entire time from 0 to 6 seconds and I busted it up into, I think, 180 pieces. So that's the increment in time. They're not spaced so that you get an integer value you might think of, all right? So that means the values of this signal, once we do the Fourier series approximation, you're going to get slight oddities, but the higher the number of terms you use in your summation, and the smaller you get the delta t, the closer this goes to a perfect square wave. Do you follow me? Now, this isn't exactly a square wave. It goes, this should be -5. From -5 to -4, it's -1. Then it goes to 0, should go to 0. From -2 to -1, it's +1, goes to 0. Does everybody follow me on this, class? Can you all see this? Now, if I wanted C of n for that, I would take only one derivative. Do you all see that? First of all, what's the period in that? Just look at it. Isn't it really from -2 to 4? Do you all see that's the period? How many do? So it's 6, isn't it, class? Can you all see that? The period for that one's 6. Now, I've got the period. What is omega naught? Or what's the fundamental frequency? If the period's 6, F naught is 1/6, right? And what is omega naught? 2 pi times F naught, right? 2 pi divided by 6. Follow me? Now you have omega naught that you're going to need. After that, you need C of n, right? Now look, I take one derivative of that. I'm going to have impulses everywhere there's a transition. They are either going up to a value of 1 or going down to a value from 1 to 0 or from 0 to -1. Follow me? The derivatives or the delta functions occur at -2, -1, 1, and 2 if the period is from -3 to +3. You all see that's my window I want to work at? I want to work symmetrically about 0. So if my period is 6, I'll start at -3 and stop at 3. Everybody follow me on that, class? Now, when I do that, let me just get to the point here. I'll show you my MATLAB code for this. And I appreciate, when this stuff looks threatening and painful, I've had to learn a lot of different languages. I've had to learn, my first language is Fortran 77. I remember programming in that. I remember you're way too young for this. Your parents, maybe your grandparents can tell you about card decks. We used to have to punch cards for every single line of code. And we'd have decks this thick. And then you want to run your code, you'd go and take that deck and give it to an operator, and he'd put it in the card stack, and then out comes all these errors that you'd have to address. Then you had to repunch all the cards that you wanted to change, and it had to be numbered. And every once in a while, one of those cards went flying and everything went up in the air, and then you had to figure out how to assemble the deck. This used to be the most time-consuming part of computer programming. I hated that. Then we got rid of the card deck, but we still had Fortran 77. It's not an object-oriented code. Everything is serial, and everything has to be formatted in a certain way, 7 spacings from the edge, then you declare your variables, and it was a pain. And we had things called subroutines. You have M functions you can call, but things kept getting better and better. There was Fortran 90, and then C, and then C++, C++, and then now you've got what? Python and Java and all these other codes that are higher and higher level languages that make it real easy to program. MATLAB is like that for engineers. It's a very high level language that makes programming very easy relative to doing it in a base language. Like, I mean, if you had to do this in C, I don't mean C++, but C, you would really be mad. My wife has to do this kind of stuff, and she comes to me complaining that they make her do it. I'm like, well, you can take a code in MATLAB and it'll turn it into C, believe it or not, into C++ and C. Does anybody know this? Remember what I'm telling you now. Now, there are some conditions, because certain things in C aren't available. I mean, certain things in MATLAB that you are going to run aren't available in C, but the base functions are, which is nice, because I can write a code in MATLAB, turn it into C, and hey, and it's not a compiled code. I mean, the actual line-by-line code. So that makes my life a lot easier if I have to create a C code. Thank God I'm not being paid to create one these days, but I've had to do all sorts of bizarre stuff in my life. Anyway, getting back to this. Remember, we had derivatives, right? The derivatives occurred, or I should say, the delta functions occurred at -2, -1, at 1, and at 2, correct? Now look here. First, the actual value, the amplitude was A. First, my period is 6, my amplitude is 1, right? The transitional height is 1. So, and omega naught is 2 pi over t. I call TF as the final time. I'm just making it one period. I'm going to actually go from minus TF to plus TF. The TF is the final time. I just use that symbol. You can use any symbol you want. Follow me, class? Next, come on down, NUM. That is the number of discrete points in time I have. I am going to take the total length, which is really 2TF, and I'm going to divide it by num, and that would be the delta T. Do y'all follow me? Now here's the way I do it, and there's so many ways. I like doing it this way. I say I want T, this would really be delta T, but I call it T. It's actually the time, no, it's not delta T, it's the increments. I use a thing called linear space. It's LIN space. And from minus TF to TF, that's the range of time I want, from minus TF to plus TF, and I want to chop it up NUM times. That's how many different discrete points there that be. You all follow me? And this is a real easy function because you don't have to do any calculation. If I want to go from -5 to 21, I put it in there. And if I want 1,000 points, just put 1,000, all right? Smart thing to do is always let the variables you're going to use in here, the num and stuff, leave it up here somewhere where you're going to define it outside of that parenthetical statement. Now, the next thing I have is I just put 180 there where you can put 150, you can put 100, and I put number here, 300. I'm going to bring it down to 100. I'm going to show you some stuff. Now, I have to do one thing here because of the way I'm doing it. I'm doing this with for loops on purpose. I don't want to do this in a complete matrix format because it may cause some of you to stumble and you'll really be wondering, all right? So I'm doing this with just for loops. Now, y'all have had C, right? Everybody here's had C, it's my understanding. So C is what? Based on for loops, right? So here's what I do. Remember what I'm really up to when I'm doing this. Matter of fact, I hate writing on this overhand, but I may have to today just to exemplify something. Let's see if I got this available here. I'm going to recreate it real quick. This would be the radar stuff. All right, let me see if I can recreate it real quick. All right, I'm just gonna, oh man, I think I got it. You don't need to write this down, just watch me on this one, all right? You really don't. And I hope I can write it down. So remember, if I have x of t here equal to a summation n equals minus infinity to infinity, and now I'm gonna have c of n e to the j n omega naught t. Y'all remember that? Sorry, it's messy. I know I can turn this into a single-sided cosine series, and that would be c0 plus the summation here from n equals 1 to infinity of 2 times magnitude of c of n, right, times cosine of n omega naught t plus the phase angle of c of n. Y'all agree with me, class? Now, we're not going to go from 1 to infinity. We're going to go to some 1 to some number, some large number. So I'm going to go from 1 here to really, I think I called that n here, n, where n is going to be the upper limit. Follow me? Not an infinite number of terms, but a large number of terms that's going to approximate it. My c0 is still the average value, right? And my c of n, right, that's just 1 over t. And then I take cn double prime, or prime, just one prime, and what is that really going to be? That's going to be a, right? And there's delta functions, a delta of, well, let me do it this way. If I want c of n prime, I know that's it's a over t times the integral of from minus 3 to 3, and here it's going to be delta of t plus 2 minus delta of t plus 1 minus delta of t minus 1 plus delta of t plus 2, I think. Wait a second, maybe I got that wrong. I got a minus, or I got a plus at minus 2, then a minus at minus 1, then I got another minus at 1, and then a plus at 2, correct? Those are the delta functions. Y'all with me, class, what I'm doing? And this has to be multiplied by e to the minus j n omega naught t dt. So when I take a look at this, my cn prime is really going to be a over t times, and here it's going to be e to the plus j2 n omega naught minus e to the plus j1 n omega naught minus e to the minus j n omega naught plus e to the plus j2 omega naught. Do y'all see what I'm doing here, class? How many do right here? Show of hands. Can y'all see it in the back? All right, now, that's Cn prime, but I don't want Cn prime, I want Cn, so I just divide that by Jn omega naught, right? So divide all that by Jn omega naught. Are you with me? Everybody? Now, listen to me there. I can do one thing by looking at this to make your life simpler. You see how this and this right here, that's a plus, that should be a minus right there, right? Isn't that 2 times the cosine of the argument there? Give me a show of hands. How many see that? Y'all see it? What's the next cosine? Isn't this one remaining just what? 2 times the cosine of n omega naught? Isn't that right? Show of hands here. Now you can put, I didn't do it, but you can put that in terms of the cosine as well, can't you, class? And that would reduce the number of calculations. Anyway, this right here is the C of n that actually goes in here, right up here. Follow me? Show of hands, class. Please be attentive here. I'm trying to do you as many favors as I can with this. Now, the question you should have is, now that I've got C of n, I know I've got to have a sum on n, right? But I have to sum that in for every single time increment. You follow me? Because what you're going to do is when you have C of n, you have to put the phase angle of C of n here, follow me? And you're going to have t will be incremented in another loop, an outer loop. T is the time increment. So the way this works, and I'll show it to you right here. When I look at this, first my outer loop in I is going to be the index on time. If you look in here, here's, I've got the cosine series in here, but if you look at this, what's that? Oh, my God, thank you. I'm so not used to using this. I hate this thing. But anyway, when I look here, you'll notice that this is C of n, but I call this x of in. Let me explain this. I'm going to take each one of the terms. I'm going back to the other cam, so hold on. Hopefully. I'm going to take each one of these things for a given value of n and a given value of I. Remember, I indexes t, n indexes the series, the summation on C of n, right? I'm going to create something that's going to be an array. I'll call it an array. And that's back here. That's right here. I call it xx of in. Now, I is the increment in time, n is the increment in the actual C of n value, right? And I just say it's 2 times the absolute value of C of n times cosine of n omega naught times t, argument of I, plus the phase angle. The phase is just phase of C of n. Now, that's in radians. Follow me, class? Everybody? This argument of that cosine, all that, that's an angle, but it's in radians. I take that and I assemble this. Now, that is a 2-dimensional array. I is going to be on the vertical plane, and it's vertically downward. Think of it that way. It's the way it's ordered. And that increments time, right? The horizontal one is n, and that increments the value of C of n. But you have this multiplicative effect. Now, once I go ahead and sum this, I create this C of in. But now, when I want to display it, I want to sum up all the values of n for a given index in time. Does that make sense to everybody? Give me a show of hands if it does. Remember, I only want one value for x in time, so I take all the single values of C of n equals 1, 2, 3, all the way up to n, capital N, and I add them all up. That's what that summation does, right? And then I put that in a single array. Now you'll notice, I just call this x. I don't have to call that x of I. Follow me? Now this summation is interesting. You're going to like this. The sum, if you've got an array that's 2 by, or say it's 2 by 2, you can sum either the columns, and I'm going to show you that, or you can sum the horizontal, actually rows, or column or row. You can actually do it, and you can get a single value. Let me actually do one thing right here so you can appreciate this a little more. MATLAB has just got so much power. Now, if I go here and I just say, I'm going to create something, A is equal to, this is the way you create a matrix. I'm going to create some values. I'm going to say it's 1, say 1, 1, 1. A semicolon puts you at the next line. Follow me? And then I'm going to say 1, 1, 1. And if I don't put a semicolon at the end, it'll display it. At least it should. It's slow because I have to have a FlexLM license, and I hate that thing. If you have your own student version, bless you. Now you see, if I want to do a sum of A, comma 1, watch. Well, this might take years. It sums up all the columns. You see that? But if I do the same thing, and instead of 1, I go to 2, now it sums up the actual row values. How many see that right there? And that's a very powerful tool. By the way, MATLAB's got so many things and tricks. And the way I always do it, I go to YouTube. And whenever I want, I type MATLAB and whatever I want to do with it. And by God, students are more than happy to tell you every trick they found out, especially the ones that are really valuable. And I don't know why people do that, but that's something about the social media out there that people love to tell others what they found out and get credit for. At least it seems that way. All right, now back to this problem we have. That's the figure. We want to reproduce that. So I've got my C of n, and I actually put the cosine form right below it. You all see that, class? Actually, I forgot the 2. Should be a 2 there times that. I'm going to do this one. So this is my individual terms, and then this is the sum. Now I'm going to bring it down here so you can see what it looks like when it's rough. Instead of having num equal 100, let's go to 50. And instead of 150, let's go to 100 terms. Now this hopefully will run fairly fast. And it doesn't look good. What's that?
This 10.
Oh, 10. Yeah, that would make kind of rough. Yeah, thank you. Well, you can all see it looks sort of like it, but what do you see? There's a lot of air and slop right at the transitions, and this is something you always be aware of. No matter how many terms you take, if you've got a transition that's hard, it goes from 0 to 1, it's there's going to be an infinite slope to that thing, you can take all the terms you want. You will always get overshoot and undershoot, and it will always rain down. You can't avoid it. It's called the Gibbs phenomenon. How many have heard of this, the Gibbs phenomenon? All right, now, your programs, the advanced one like PSpice and stuff like this, or LT-Spice, they know that ahead of time. So whenever they see that, they automatically clip that overshoot stuff, all right? Now, there is a thing called a real ringing that occurs in the circuit, but they'll get rid of the Gibbs phenomenon. Now, watch what happens to this thing. By the way, one other thing I didn't tell you. When I wrote this code, you see these three things on top? Clear all, close all, and CLC. Clear all gets rid of all the memory, everything in memory. I always do that because half the time I forgot what I stored in memory if I write MATLAB code and I got 3 or 4 subroutines out there. Follow me? So I clear everything out. Next, the closeout closes all the windows, all the displayed windows, the plots and all that. And I might have 10 plots sometimes. I've got 3 screens going, and I have radar, Doppler radar shifts, the bins, and I have all sorts of stuff. And usually I do this so I'm not looking at old data, because I'm notorious for forgetting to shut something down. And I know myself, so I do this. And then the CLC brings up a completely new page in the command window. How many knew those commands, or at least some of them? This is vital for me. Now, they probably have one single command that does everything that I don't know about, but that's how I do it, all right? Because I'm old. Now, watch what happens when I go from 50 to 200, or 200 terms here. Now you're still going to see weird overshoot stuff, and then we're going to change the time. Come on, run. One thing you can see is now it's a lot crisper around the edges, right? You don't see that apparent overshoot that bad. Follow me, class? Y'all see it in the back there or not? I'll blow it up if you want me to, but anyway, you can see that you still got some weird effects going on here, and that has to do with the differentiation in time. But now when I go to time here, let's go to 300. I don't know how long this is going to take, but hopefully. This is a relatively trivial problem. It's just this FlexLM makes it a notorious. Now you can see the overshoot that I'm talking about, because now we're hitting right at that point where that overshoot occurs. Do you all see that right there? You will never get rid of that 100%. All right, I'm just telling you that. It's always going to be about a 6% overshoot when you get a hardcore transition like that. You can kill it, though, other ways. And there's books written on this stuff. Just for the heck of it, I want to do one more thing. I'm going to try this at 300 as well and see what happens here. I'm curious myself. Looks better. Am I right? Yeah. That's still that overshoot. You're never going to get rid of that. But here's one thing. Another thing you can take a look at. Now that was with the actual exponentials. Now I can go here and just take it with the cosine when I complete it, when I go ahead and assemble them in terms of cosine, class. Follow me? And it's the same thing, but one thing you should have noticed, it ran faster. There's less calculations when you combine things into terms of a cosine. All right, so that's something to keep in mind. You basically combine 2 exponentials into a single function, which makes it a lot easier to do. All right, now that's actually not too bad. That's looking pretty good to the actual squares. I mean, it was a perfect square wave that I tried to get there. Now this is all with simply an input voltage that looks like that. All right, now we're going to put it through a filtering effect. Let me do it up here so you all can see this. Then I'll go to the board, and I'll answer any questions. I hope this is helpful. Now what I'm going to do is take that value of x of t. Yeah, I know. Now I know. All right, now what I'm going to do is this. I'm going to say this is the x of t, my x of t that I've got there, and I'm going to put it into a filter. I'm just going to pick a filter. I'm going to create one, all right? We can have any kind of filter. I'm going to make the simplest possible thing, an R and a C. Doesn't get much easier than that, right? So I'm going to put an R here, and I'm going to put a C here. Let's make this easy. Let's put R equal to 1 and make C equal to 1/3. That's pretty easy, right? It's also a very large capacitor. You're not going to find that hanging around in the shop. 1/3 farad. If it's got 100 volt max on it, it's huge. But anyway, that's our thing. What we want to do is get the voltage out here. plus the minus V out. Right there. Really, you could say this is V in. Are you with me, everyone? Class? You see what I'm up to here? Now, this is a pretty easy response. First of all, we're going to go into the frequency domain. What do you know the reactances or impedance of a capacitor in the omega domain? Anyone? It's just 1 over j omega, right? Times c, right? But we don't have an omega, we have n omega naught. Understand? We're going to be at discrete frequencies. So now we put n omega naught down here, and then we put c. Everybody got that? And if it was an L, we put what? J n omega naught L. It's not omega, it's n omega naught, right? Omega naught is the base for fundamental frequency, and n is the index. If you're at the first harmonic, it's just omega naught. Second, it's going to be 2 omega naught, and so forth. How many understand that? Now, when we want the transfer function, h of, call it n omega naught, what I want is really V out of n omega naught over V in of n omega naught. You all see that? What is that? I mean, what are you going to do there? What kind of, if that x of t is a voltage, what am I going to do to get the output? Voltage division, right? I take the impedance of that capacitor, and then I divide it by the impedance of the capacitor plus the resistor, and I take that, which is h of n omega, and then I multiply it by the input. But first of all, for h of n omega naught, that's just equal to what? 1 over j n omega naught times c over 1 over j n omega naught c, right? Plus r. Do you all see that? I'm going to go a step further. First, how many see that right there? That's a ratio of output to input, isn't it? Now what I'm going to do is this. I'm simply going to multiply top and bottom by j n omega naught c. Why would I do that? Make it as just one term downstairs that has the variables. Follow me? So if I multiply top and bottom, then I get this. Right here, equal to 1 over, and then it would be 1 plus j n omega naught r times c, and that's a time constant. Isn't that right? Now you all see that's generally a complex number, isn't it? Which means it has a magnitude and it has an angle. And thank God, MATLAB can do this for you very easily. I can show you that the magnitude of this, because you'll have to do this, if I want the magnitude of h of n omega naught here, that's just 1 over square root of 1 plus n omega naught rc squared, right? You all agree with that? Show of hands, how many know that that's the magnitude? You take what? The real part and square it, the imaginary part and square it, and take the square root to get the magnitude of a complex number, right? In general. 1 on top is just 1. You don't need to do anything with that. Now, if I want the angle, by the way, how would I get it? The angle of h of n omega naught. Well, what's the angle of 1? 0 degrees. It's 1 at 0 degrees, right? The angle down here would be 1 over, and then it would be that what? When I look at the angle of this, it's the inverse tan, isn't it? Of opposite over adjacent, correct, class? So this is really downstairs, it would be tan minus 1 of n omega naught rc over 1. And if I have, that tan minus 1 is inverse tan, by the way. Sometimes you see it as a tan. How many know that? All right, just make sure I know that you know. Now, when I take a look at that, and I take 1 over this, now this is an angle. So that means this becomes minus, and then it would be tan minus 1 of n omega naught r times c. Y'all understand that if I have an angle downstairs, if I have, say, in the denominator, if I have 1 at 40 degrees, when I take it upstairs, it's 1 at what? Minus 40, isn't it, class? Everybody understand that? That's why I put the minus sign. People forget that all the time. Trust me on that one.
How did you get the inverse tangent? I don't see your logic.
Right here? Well, this is how I did it. If this is j n omega naught rc, and this is 1, and I want this angle, don't I? Isn't tangent the opposite over the adjacent? So the opposite would be n omega naught rc, right?
Okay,
And the adjacent is 1, isn't it? That's the real part.
That's the angle of transfer is j n omega naught.
If I have a plus jb, right? What's the magnitude of a plus jb? Just tell me.
Square root
A squared plus B squared square root. How many know that? What's the angle associated with that? It's the inverse tan of B, right, over A. Isn't that right? All right, what did I do here? My B is like n omega naught R times C, isn't it? It's the coefficient of J. All right, and A is like 1, right? You all see that, everyone? So this is how you would get the angle. Now, technically, I'm just going to tell you what happens here. You all realize that's the CNN, or CNN, C of N. Listen to the news team. So now, if I want to write the series down, right? I mean, put it to you this way. Now, if I want my output voltage, let me get to the point. Understand, class? If I want my output voltage, my V out of T here, that would be C0, that's the DC value. By the way, what was the DC value for the actual waveform I showed you? What do you notice about the area above 0 versus the area below 0 for a period? It's 0. How many say that? Those are the kind of waveforms we like. There is no C0. It's 0. You can't mess up. That's the reason I didn't add it on there. Follow me, class? Now, when I look at this, it would be C0 times the transfer function evaluated at n equals 0, right? Plus, then it's going to be, write this down. I put this up last time, but I want to make sure you write it down. Don't forget this. And we're going to do it here in a second. Plus, it's going to be the summation, right? And now we have n equal 1 to infinity of 2 times the magnitude of C of n. We have C of n, correct? Now it's going to be the magnitude of h of n omega naught. And we have h of n omega naught. We can get the magnitude. I put it down for you. You all agree with me, class? Then it's going to be times the cosine of n omega naught t. Remember, t is a function of I, right? It's, the index is I. But I'm going to crop all this up in here, and then I'll do it in MATLAB in a second. Then once you get that, you have to add to it the phase angle of C of n, right? As it's just phase. Phase is the MATLAB command for that. By the way, how many have used, what is that, Wolfram Alpha? How many have used MathCAD? Anybody? I use MathCAD all the time. Anybody use Mathematica? Here? Mathematica is powerful as well. There are many other languages. Now, MATLAB personally is the most powerful matrix manipulator I know of. But as far as displaying things easily, MathCAD is much easier, and probably Mathematica too. It's much easier to do. And those languages are, and I know Wolfram Alpha, that's not something you have on your computer. You have to, it's a web access thing, right? But you can do these things on that too, I understand. I don't use that much. I'm just telling you what's available for you. Anyway, now, when I look at this, it's going to be this angle. Then it's going to be plus what? The phase angle of h of n omega naught. Now, all those things are inside the argument of the cosine. How many understand this? Remember last time I did this on Friday, class? And I put this up here. How many remember that? All right, if you were here, you should remember it because I spent some time developing it. Do you remember how I got the single-sided cosine series out of the double exponential, right? And then I showed you how h of n omega naught would work into it. Didn't I, class? Because of the phasor domain. So please be aware of that. Now, what I'm going to do is take this right here and program it there. Understand? But we're going to do it for that crazy transfer function right here. And I want you to just watch how easy it is. This is the crazy transfer function, this one. And what is RC? RC is just a third, right? So what I'm going to do, just go back to this and yell at me if I forget something. I have to push that button. So work with me here. Now this is MATLAB. Oh, one other thing I'm going to tell you. And by the way, if I forget to tell the class something, jump in if you know MATLAB. Just let me know. You see this, this little percent sign right there? You all see it, or can you see it? Anything after that is a comment. So every language I know of allows you to put comments in, where if you want to write something in, because I mean, my old codes are just, I've got line after line of commentary about where this is useful, what subroutines you plug into, all that. So I put that there, and I can say anything. I can say this is the period. Period. And it won't give me an error. But if that percentage sign isn't there, it's nice that it shows in green too, so it identifies, it color codes them, then I get an error. And I get lots of errors when I code it. All right, there's the fundamental frequency, the final time, the number of steps, the number of terms. And now I'm going to put in a few others. And this is one other thing that's nice. I don't have to put stuff on the next line. I can just say that RC is a value, and that equals, I can just say equals, what did they say, 1/3, right? But then if I don't want it to repeat itself or prop up in the command line, I put a semicolon. That means it will not represent itself when I run the code in the actual command line. Understand? When you're in command line, that's where all the errors prop up. And if you've never seen errors, you're going to see some. That's one thing I specialize at with MATLAB. I get more errors than I get anything. All right, now here's the basic thing so far. Now, what do I need to do? I need, first of all, to create h of n omega naught, right? I've got my omega naught. So what is h of omega naught? I'm just going to use small h. H of, I'm going to call it h of n. I don't have to put the omega naught in here because h of n is like the capital H of n omega naught. Understand? Because the only thing it indexes on n. What was that equal to? It was 1 over what? 1 plus, and here's the other thing, when you put a J in, you put a 1J, just 1 and J right next to each other, or 1I. You have to put that 1 in there, or it gets irritated with you. All right, so when you want to put a J term, it's 1J with no multiplier. Understand, class? 1J times N times omega naught, right? Times RC. Notice I didn't multiply R and C together by because what? What was the reason? I know it's always going to be a product. I don't need to have them separate, right? For this one. Now, something else I'm going to tell you. If I left it like that, I believe I'd get I got to put a semicolon. I believe I'd get an error, and I'll tell you why. Well, for this one, I may not. But you notice how on top I have 1, which is a 1 by 1, right? And downstairs, I'm dividing by 1 by, in that n variable. Now, if n is a matrix operator, I'll get an error because I'm dividing a 1 by 1 by an n by m, maybe. Follow me? But there's a way to get rid of that. This is what I usually do. I don't think I'll get an error there. See where that 1 is? If you put a dot there, and I'll say more on that, that will get rid of all the matrix problems where you're doing, now it'll divide term by term. I'll say something more about this in 1 second so you can appreciate it. I'm going to take it out just to show you. Y'all agree that's h of n there, class? Now, what do I have to do if I want the output instead of x of x? Well, let me leave that x of x in there and just do this. I'll highlight it, Control C it, right? Come down here, Control V, hopefully it'll put it in there. And then I'll comment that out right there, if I can. So I'll put a percentage sign. All right, now I'm coming down here, and instead of XX, I'll call this YY. And then what I'm going to do is say, well, it's 2 times the absolute value of C of n, right? Times what? ABS of what? H of n, right? Right? Because I need the absolute value of h of n omega naught, which is h of n. How many see that? Now, what else do I have to do? Inside here, I have to do one thing, don't I? Phase of what? Of h of n, right? Of n. And if my eyes are a little better, I think that'll get it for me. I'm not sure. Y'all with me, class? Now here, what I can do, actually what I can do is get both of these. I can leave that as XX. I can leave it there, I hope. And then I'm going to have X here, but I also have Y equal the sum of YY, comma 2, right? Semicolon. And then the plot, you see how I plot T comma X? I didn't put, you can label it, now I'm going to comma T, comma Y. So we'll get both of them on there. That grid on allows me to have a grid, and I can space it any way I want, and I can label these things. The nice thing about these, the X and the Y will be color-coded. Y is the output, X is the input. Follow me? Let's see what happens. We may get an error. That H of n, I don't know. We'll see. I'm good at, got one. There it is. What does it say? Invalid expression.
Missing a parentheses on the YY function. Very nice.
Thank you. Better? I don't know. Didn't go away.
Yeah, it could be able to recut the
What's that?
Riley in
What did you say?
there. Just hit run again.
No, I don't have a pound sign. I don't have a multiply. Asterisk is multiply. Follow me? I just had the things H of N just grouped right against there. I didn't know what to do with it. The asterisk is multiply. I don't know if this is in C, is that multiply or not? It is? It is in most languages. So now I've got that, let's see what happens. Is it running? It should say busy somewhere. There it is. All right, let's take a look. So the blue is the input. You can see the red is the output. The very first thing you notice is it looks like that capacitor is just what? It's really trying to just damp down the rate things change. It allows things to sort of settle, come up slowly, and then decay slowly. Follow me? Now, the characteristics there is that of a low-pass filter. When I have my capacitor on the output, it's passing the low frequencies, right? But if the frequencies get higher and higher, the capacitor looks a short circuit and all the voltage is developed across the resistor. Do you all follow me on this? Now I'm going to see what I'm getting at here on this one. I mean, with this example, I've got a transfer function. I let MATLAB calculate the magnitude using the ABS. I let MATLAB calculate the phase using the function phase, right? And I added the phase into the argument of the cosine, right? But I had to multiply the magnitude of H of N times the C of N stuff. Everybody see that? And it's in terms of a cosine. Now this is a very powerful tool I'm showing you, because that means for any periodic waveform coming in, you can get the output very easily by analyzing the value of C of N for that periodic waveform and putting in terms of a single-sided cosine series. I'll admit I did not put a C0 on there, but you can easily put a C0 and an H0 right here. You see where the sum is, y and x? You could just have, if you wanted the C0, you could put plus, you could have this plus C0 here, and for y, plus C0 times H0. Do you all follow me? You could just add those terms. How many see this right here? And that would take care of it. Are we together on this? So what I gave you for homework, if you looked, were a bunch of different circuits with different inputs, correct? And the only thing you had to do is find H of N and C of N, and then bango, that's it, all right? I'm going to give you some homework for Wednesday, and this is an extra credit assignment. And I'm going to give you a base code like I got right here so you won't go nuts. And I'm going to allow you to have some creativity. You're going to figure out how to label it. Doesn't take but a second on YouTube. You're going to find out how to do things, and then I'll collect that and I'll give you up to 10 points. It'd be like an extra quiz, all right? And the one that gets, if this you do a good job on here, the one that gets thrown out will get replaced by this, if you follow me. Understand, class? All right, now I'm not done yet, but at least I'm done with this.
Do you want a printout or do you want to turn it in?
What I want is, yeah, that's a good question. Now, MATLAB you have available to you downstairs on the computers here, right? Does everybody know that? MATLAB is something you have to have an account with the university in order to use it here. So everybody should have an account here. You don't have to do it, what?
There's also Octave, which is just free.
You could use Octave. Oh, yeah. Octave, you can ask these guys. They'll give you a spiel about Octave, apparently. I like Octave, too, for one reason. But I can't, see, Auburn University, it supports MATLAB. And so I suppose I could, if this is my graduate course, talk all about Octave or Python. And I don't mind that. But we've got licenses for MATLAB. So I'm going to appreciate if you write it in MATLAB. If you're going to do it in Octave, it's fine. It's the same thing, really. Octave's free. Octave doesn't have the horsepower that MATLAB does. It doesn't have all the toolboxes. It's not as efficient, but it does the same stuff. How many have heard of Octave besides these two guys? If you want to use Octave, go ahead. I mean, it's free, right? I think.
Yeah.
And you find there's nothing here that's tough. We're not calling up toolboxes to do Doppler radar processing, so it's fine. You can use Octave. If you want to write it in Python, do it. But the problem with that is my grader's going to curse me. And he's already mad at me. But, yeah, keep it in MATLAB or Octave, the assignment. Now, I gave you some homework. Did you have any questions about the homework before we get on? All right, I mean, I don't know if you did it or not. It's always that Monday question, well, what percentage of class? 10% or less did the homework. How many did it? Right? If you went through it, they were fairly straightforward things, right? It was simply getting C of N. Did you use the technique I showed you to get C of N? God bless you, because if you'd used that other crap, you were going out of your mind with some integration by parts. Yes, sir.
How would you find C0 or H0?
C0 is the average value of x of t, right?
Okay.
What does average value mean? It's 1 over t, the integral of x of t dt. It's just the average value of the function. How do you get an average value? You integrate a function, right? X of t dt, and then divide it over the span, the t, the period. That's the average value of any function. Doesn't matter what it is. Yes, sir.
So how did you want that, like as a printout or?
Yeah.
Okay.
I want the code that you have printed, and I want the output, just like I displayed there, 2 cycles. I want the printout. I want your name on it. Now, I'm asking you not to collaborate. I can't prove collaboration. I prefer not to get into this argument with students about this, because if you want to work with somebody, fine, just don't copy their code, all right? Learn something about this, and I'll tell you the real reason, because on the final exam, I haven't done this in a while, but I think I'm going to put a question on there related to MATLAB. And if you've done your own work, you'll be able to answer it. And if you haven't, you won't. And that way it'll assure me that at least I used MATLAB and it required you to understand MATLAB for some credit. I'm supposed to do that. But. All right, class, now, I still got 4 minutes. It's a miracle. Yes?
So you don't care if we work together as long as we don't just straight copy code.
Yeah, and listen, one thing about computer coding, I found this out. I have been in your shoes years ago, admittedly, but I've been in your shoes, and I've actually, in day-to-day life, I'm always in a process where I'm working with people. Many times, things you don't see, your friend does, and vice versa. So if you collaborate, especially when you're thinking through how to do crazy stuff, like if I ask you to do something where I want the output here and here and here displayed all on top of each other, then you can talk amongst yourself. I'm going to ask you to label the axes, all right? I want time and the voltages, but I'll come up with something that's reasonable for you to do and meaningful. I'm not trying to just beat you up. I'm trying to get you to actually learn something. Now, is there any other questions about the homework? Because I'm telling you, I've got like 3 minutes. I don't feel like getting in, and I don't think it would be beneficial to get into the DTFT, but let me tell you where we're going so you know. We have done convolution. We have done Laplace transforms and applied Laplace transforms to fabricating circuits. Understand? And we've done op-amps with them. So we beat them up, and we've got a fairly good handle on that in filtering. We've also done Fourier transforms, and we talked about the power of duality, right? And we noticed the Fourier transforms are basically Laplace transforms for most of the crap that we have, right? We just take the S and turn it into J omega. Do you agree with me, everyone? Now, we've done Fourier series analysis because that's important as a periodic function. We have gone through that. The next point is where we're always working in the direction of modern signal processing. Now we're going to discrete time Fourier transform, the DTFT. Now, instead of having continuous time, we're going to take time and chop it up at discrete points, all right? And now those values we're going to start analyzing. So we're sampling signals. You're going to see this goes into right by the end of the course. You're going to be doing stuff where now you are literally doing digital signal processing in this course. And by the time you get to your digital signal processing course and some of your higher level courses in communications, you'll have all the necessary theory. Now, you may not understand Bessel functions and stuff like that are used. You don't need to for this, but you'll understand the theory of how the processing goes about really extracting information or creating filtering properties. Enjoy yourself. That's your book, right?
That's Victor's.